Okay, so it's my pleasure to introduce Professor Jennifer Choy, today's speaker, who is the Dugald P. Jackson Assistant Professor in PCE at Wisconsin-Madison. Jen earned dual bachelor degrees in nuclear science and engineering and physics at MIT in 2007, and then got her PhD in applied physics at Harvard, working with Marco Longbar. And then from 2013 until 2018, she worked at Draper Labs, becoming a principal member of the technical staff before starting her independent academic career at Wisconsin in 2019. She's won a number of awards starting there, including recently the NSF Career Award. And her lab has been producing exciting work relevant to quantum sensing with distinct platforms. So both cool neutral atoms and solid state color centers. It seems like maybe we're going to hear about one of those today. So I and the rest of us look forward to learning more. And so help me in join me in welcoming Professor Choy.
Yeah, thank you. Thank you very much. Thank you, everyone. Can you all hear me okay? Okay, I assume yes. Please let me know if that's not the case. So it's a pleasure to be here. Thanks very much for the invitation and for having me and for being here. So today, I'll talk about some of my lab's recent work on developing quantum sensors, primarily in a solid state platform, but I will also discuss a little bit about our progress with quantum sensing using neutral atoms. So I want to start the talk by thanking the people that did the work, which is my group, some of whom are actually not pictured here, but then also our collaborators, in particular from Mikhail Katz's group, collaborators from Lawrence Livermore National Lab, Argonne National Lab, and also our friends from chemistry, in particular, Bob Hamer's group at UW-Madison. Okay, so just to get us all on the same page, the quantum sensing that I'm going to be talking about today primarily is referring to the use of discrete degrees of freedom, and it could be as simple as just discrete electronic transitions that you can find in quantum systems such as neutral atoms or trapped ions, or the analogs of these quantum systems in the solid state, which are these spin defects in solids, and we're going to be focusing on diamond color centers. And the reason why these systems are especially great for sensing and metrology are because they have deterministic and strong dependencies on external environments. So specific transitions that you pick can have high sensitivity to the things that you're trying to measure, whether it be magnetic field, inertial motion, or temperature changes. For the most part, you can actually just measure these sensitivities using optical and RF measurements, which tend to give you high signal to noise measurements. And also it's a good opportunity for bringing in tools from integrated electronics and photonics in order to miniaturize and ruggedize sensors. And another aspect I would like to emphasize today and in the talk is that you can actually, for your sensor, access different length scales all the way from atomic scale to macro scale. So that could be centimeter, meter scale, or even larger than that. And of course, since these platforms are quantum in nature, you can also leverage quantum phenomena such as entanglement, which can improve measurement sensitivity. And all of these in combination have allowed us to develop as a community to develop sensors that provides the state-of-the-art stability and precision in terms of being able to measure time and in timekeeping applications, to sense the smallest magnetic fields, and as well as detect very small inertial forces to the point where you can start testing fundamental, perform fundamental tests of, for example, the equivalence principle between gravitational and inertial mass. So what I want to cover today is first provide a couple of examples for bulk and nanoscale sensing in solid-state quantum emitters, in particular color centers in diamond, actually in particular nitrogen vacancy centers in diamond. Then I'll talk about some of the challenges that must be overcome in order to effectively utilize these sensors. And that involves both some chemistry and some optics. And this later part of the talk will be a discussion of a integrated photonic platform based on thin film single crystalline silicon that can be used to better extract light and also enhance light matter interaction between your photonics and quantum emitters. And I'll provide examples of that both for the solid state emitters and for the neutral atom work. Okay, so a quick introduction on vacancy defects in solid state crystals. In particular, probably the most popular one of which is the nitrogen vacancy center in diamond. So what that consists of is within the diamond lattice, you have a missing carbon atom, and next to it, which we call the vacancy, and next to it a substitutional nitrogen. And this defect leads to a set of unpaired electrons that exhibit a ground state triplet state. So this is the corresponding energy level diagram for which the ground state is a triplet with spin states ms0 and ms plus or minus 1. It is optically active, which means that if you excite these unpaired electrons with, for example, a green laser, but basically you can do this with any above band excitation. Across this pure optical transition, you get then fluorescence out, and that comes in the form of red light. The pure transition is at 637 nanometers, and we call that the zero phonon line. And as the name suggests, phonon activity is a big consideration in this diamond crystal. And the emission that you get, especially at room temperature, due to a phonon relaxation, basically it's fairly broad, goes all the way from this pure optical transition at 637 nanometers all the way to 800 nanometers. And the nice thing about this MV center is that it is optically, you can polarize it optically. And the way that happens is through these intermediate metastable states, which has different non-radiative decay rates from the spin states. So a common operation involves just continuous excitation of this energy system with green laser. And through many, many cycles, because of preferential relaxation non-radiatively of the electrons back to this ground state, ms equals 0 state, you have then polarization of the MV center at ms equals 0. And this is also the mechanism by which you have optical readout that is dependent on the spin state, namely that you get more fluorescence if your spin is at ms equals 0 versus ms plus or minus 1. So this ground state is also useful for sensing. So the separation between this ms0 and ms plus or minus 1 is by 2.87 gigahertz. In the presence of a magnetic field, you have basically splitting in this subsystem. And you can actually measure that optically. So this is a spectrum of the magnetic resonance as you're scanning over this transition. And the splitting that you observe is going to be magnetic field dependent. And the reason why you see 8 dips here as opposed to 2, which is what you would expect for a single MV center, is that the MV center has to be grown along the crystallographic direction of the diamond. And it can actually be grown along any one of the 4 possible directions in this tetrahedral structure. And so then you get 4 orientations. And so if you have a magnetic field that has projection, non-zero magnetic field projection along any of these directions, you see different a splitting, and they can be made to be different. And so then basically you get a vector magnetometer for free with your coordinate system of your magnetic sensor being referenced to basically a diamond crystal. So the way that we make these diamond color sensors as a community is could be done via growth, introduce these defects during growth, or it could be done after you have already grown the diamond and you utilize ion implantation. So you typically start with either very clean diamond, so to the point where you're less than 1 part per billion nitrogen, or here, as I've shown, you can also start with diamond crystals that are intrinsically like pretty rich in nitrogen, and this is when you get yellow diamond. And then you can send the sample out for implantation services. You can actually do this with nitrogen ions. You can actually also utilize native nitrogen inside the crystal and just introduce vacancies with neutron and electron irradiation. So we have, I have examples of all of these approaches. So yeah, in one case, you would just bombard the crystal with nitrogen ions. There's a picture of our ion beam lab at UW-Madison. We collaborate with Sandia National Lab to basically utilize focused ion beam, which is a variation of this technique that you see up there. But then the idea is that you have beam focusing optics for your ion beam, so you can get to place your ions where you want up to a point within the diamond crystal. And then there's actually a picture of our nuclear reactor. You can see the Cherenkov radiation in at UW-Madison. We've also stuck diamonds inside this nuclear reactor to generate vacancies. And then after that, what you do is, so you have vacancies. That means that many carbon atoms are being knocked off. Some of them are randomly close to a substitutional nitrogen, but not all are, right? So your crystal is pretty damaged. So what we do is we heat up the crystal through this annealing process, and that mobilizes the vacancy. So the crystal is healing itself, and then the vacancy can also find a nitrogen. And when that happens, you have a good chance of getting an NV center. And after that, after annealing your crystal for some time, you get a certain amount of gravitization on surface that you then clean it up with chemicals, with acids in particular. So just some nice pictures showing like what you can make, right? So the nice thing about making color centers is that you actually get nice colors out of an implantation run if like they're dense enough. So what you see in this picture here are the high pressure, high temperature diamonds. The yellow one is the nitrogen-rich diamond. And then after we stick it inside a nuclear reactor and anneal it, it actually turns a little dark. But then if you shine it with green irradiation and put a filter over it, you actually see this really nice red fluorescence. You can kind of do the same thing with UV light. And you can also ion implant with nitrogen onto a ultra pure diamond crystal. And so you, depending on the dosage, you get individually resolved color centers, and combine. You can also combine that with some kind of nanofab to isolate these defects. And then these are the bottom pictures are a couple of images shown of FIP implanted, in this case, silicon vacancies. So I mentioned that I'm going to talk today about very simple types of quantum sensing, which are ones that are based only on discrete electronic transitions and not really leveraging any quantum entanglement. I'm going to actually start. The first type of sensor that I will talk about is even simpler than that. We're actually going to go with a zero field and microwave free magnetic sensing. And here we are actually not focused on sensing by any individual NV sensors. We're going to focus on kind of bulk sensing, trying to use the entire diamond crystal as a sensor. And so this is a concept for which actually the Butker group at Mainz has done a lot of nice work in, and I actually recently attended a talk by Dima Butker, and he mentioned that this as like a primitive magnetic sensing method, which I like a lot. So the idea is that you don't need to apply any microwaves, and you're just relying on the fact that under a non-zero magnetic field, the energy level system that I was showing in earlier slides consists of this ground and excited state triplet, right? And then this singlet state is the intermediate state. The green here represents the excitation, the red represents the decay. And if you were to apply magnetic field, you actually end up getting, as a function of magnetic field, changes in rates of this decay, in both the pumping and decay rates. And at some point, you have basically crossing. So this is called known as a cross-relaxation phenomena. And what that means is that your photoluminescence that you get, like which is the level of fluorescence that you get at a particular pump power, is going to change depending on the amount of magnetic field applied. On the right here is a spectrum that shows the change in this photoluminescence as a function of magnetic field. The exact level where all of these transitions cross is actually at about 100 millitesla. This feature here is due to contributions. So if you're looking at ensemble MV magnetometry, this is due to contribution from other spins for which that is not along this direction of the magnetic field application. And so then this provides, even though you're looking at several percent changes in the photoluminescence, this provides actually a pretty nice, easy way to actually measure magnetic field. And so I had this opportunity as an advisor of the rocket team at UW-Madison to actually come up with a payload that we need to send up a sounding rocket, and we needed to do it under budget, like about 1.5K or so. So actually my team and I, we came up with just trying to utilize this approach and package it the best way we can, and to send it up a sounding rocket as an example of a magnetometer that you can potentially eventually deploy in space. And so this is some of the work that we did. This is a team, they just launched this rocket this past June in a spaceport, America in New Mexico. And this is their rocket. Inside a rocket, we have a scientific payload that's part of the competition, where it's 3 U. So what that means, so each U is a cube set, so it's 10 centimeters by 10 centimeters by 10 centimeters. And we package a diamond that's rich in MV centers. And we use a green LED to excite these diamonds. And so what comes out will be red light. And then we filter out the green LED through a long pass filter and just directly stick a lens and photodetectors. It's the simplest way we could actually package an MV magnetometer. And because this particular primitive magnetic sensing is not the most sensitive, we actually ended up having to apply our own magnetic field to show that it works. So we have also Helmholtz coils here. The whole thing is battery operated with custom electronics. And this is a picture of the rocket being launched. It went up to well over 10,000 feet. The rocket team actually won an award for their packaging of the payload. But I want to actually cover a little bit of the data that we were able to collect through that whole time. So we're able to get nice data through the entire entire operation, all the way from when the team first loaded the rocket onto the launch pad and then waited hours under 100-degree weather, 100+ degree weather, and then eventually got launched, and then eventually they recovered it. And so the whole time our sensor was working, and we were able to have simultaneous data for the acceleration, so that we know when launch happens. Launch happens at this spike where it goes, the acceleration along y, which I guess must be in this vertical direction, goes up to 10 G. And then during this time, it actually activates the sensor to take more data. But then what we were doing the whole time is looking at the optical change as a function of the applied field to basically show that you get this nice linearity that's consistent. So a couple of other funny things that I guess only matters when you're trying to package sensors. We found a nice temperature dependence of our photodiode signal with the internal temperature, which actually doesn't really affect the quality of our data because we were doing this on and off switching of the magnetic field. So we're able to calibrate basically continuously. And then this is the zoom in of the data during the flight, which, all these steps of the photodiode is basically when we turn the coils on and off. And then during this time, we can collect data on the optical change as a function of the applied field. It shows the same slope as during the rest of the sequence, showing that our rocket remains functional this whole time. And so, so this was our first experience in sort of packaging this type of all optical sensor. And even though the sensitivity that we have here are not great because we literally didn't spend any time trying to optimize the amount of light that we're getting, a sensor like this actually could be useful for eventually doing magnetic surveys, geomagnetic surveys, and navigation to measure magnetic field changes due to crustal features. I should have swapped out the map of Wisconsin here for the map of Illinois. And then there's now a subfield in terms of developing navigational instruments that are based on magnetic navigation. So it's the idea that these crustal variations that are leading to magnetic changes are not going to be changing over long periods of time, right? They're going to be pretty stable. And if you're able to drown out all the ambient noise, like by actually moving above ground, which is why you do need an aerial vehicle to do that, then you can, and if you have a very good magnetometer, then you can actually make better maps and then also use these maps for positioning. And as an example here, this MagNav project that is an initiative out of Air Force and also in collaboration with MIT is the idea of applying artificial intelligence, machine learning techniques in combination with existing sensors in order to achieve good positioning. So you can imagine that using high quality quantum sensors that are stable and reliable would really be able to help. So now I'm going to switch gears a little bit and talk about moving scales from bulk sensing to basically spatially resolved atomic scale sensing. And a couple of examples, and Professor Beckman has also done some beautiful work in like using MV sensors and similarly quantum emitters to basically achieve nanoscale level detection and imaging of changes, for example, in cells, in this case, and also changes in magnetic field. Another application that I'm quite excited about is basically the use of these color sensors for diagnostics of materials. This on the right here is an example of being able to do electric current imaging by doing vector magnetometry and spatially resolved vector magnetometry of a sample that's placed on top of an ensemble of color sensors. Other examples include being able to do nanoscale thermometry, but then doing so in an all optical manner, which when you're talking about biological sensing, that could be very useful because microwaves can heat up cells. And then another application is basically the use of color sensors, and in particular, the radiative lifetime of these color sensors in order to study the energy features and energy transfers with nearby fluorophores. So for all these applications I mentioned, whenever you need this spatial resolution, you actually need to deal with near surface quantum emitters. And by near surface, we're really referring to within kind of 10 nanometers away from the surface. And there, in the solid state world, that's actually not the place that you really want to be. And because you have various challenges, optical and chemical. On the optical end, your emitter have dipole moments that are pretty much stuck in orientations that depending on the crystal. So you have to deal with that. It's not like, if you trap an atom, you have a much cleaner dipole moments that you can analyze. And then also these wide bandgap semiconductors that are host to good quantum emitters because they're they also tend to have relatively high refractive index. So light actually tends to get trapped inside those crystals. And then if you're talking about using these quantum emitters for sensing, it's actually really often difficult to control the surface chemistry in a way that will aid your measurements. And diamond in particular is a great stable material, but that also means that it's a very inert material, hard to functionalize. And there's also a lot of observation, and that's all summarized in this plot here that shows that if you're dealing with near surface emitters, the closer you get to the surface, the more you have decoherence basically in your emitter, and that's just due to surface electric and magnetic noise. So the next part of my talk is going to be on some of the work that our group and our collaborators have attempted in order to address this problem. So a very quick example is this work that's led by Bob Hamer's group at UW-Madison on basically grafting carboxylic acids onto the diamond surface by starting with a clean surface. So what you really want is you have a diamond crystal of a particularly known crystal orientation. And so you can clean it up by actually just hydrogen terminating it. So then the picture that you can have, well, in terms of what's happening on an atomic or molecular level are these like hydrogen bonds that are just sticking up nicely. And then you come in with carboxylic acid, and it could be different lengths of the chain. And then this actually enables you to help graft tempo, which is a stable free radical that's very useful for bio sensing onto the surface. So this is work that's primarily led by Bob's group, and this would enable nice way to repeatably functionalize the diamond surface and potentially functionalize with biomolecules. Another reason that I've alluded to as to why we care about the surface chemistry of diamond is that the type of NV center that we are primarily working with is the negatively charged nitrogen vacancy center. As the name implies, right, it has it's negative charge because it has two unpaired electrons. And it actually likes to see in its environment something called a positive electron affinity, which then tends to allow for it to keep the charge. And so in addition to charge stability, having this positive electron affinity on the surface also allows you to have better spin coherence for your NV center. And there's a really nice work from various groups, including from Natalie De Leon's group at Princeton, that shows that if you apply the right surface termination, oxygen termination, you can really improve the spin coherence time of these near surface color centers. But what we've noticed is actually there's a great deal of inconsistency in the reported oxygen coverage in the literature. And here's one more piece of information that we'll come back to later, is that in addition to just oxygen content on the surface, which gives you positive electron affinity, there's also observation that if any graphitization or amorphous carbon on the surface is going to affect your spin behavior. We'll go back to that later. So something that our group started doing is basically coming up with a set of rigorous surface preparation methods, and also coupled with XPS analysis. XPS is X-ray photoelectron spectroscopy, where you're sending in X-rays and to knock off electrons off the atoms near the surface of the sample, and then the energy of these electrons gets analyzed. And this work done by my now PhD graduate, Ricardo Vidrio. So one of the things that we first did was try to understand why we see so much variation in the reported values of these oxygen content in literature. And what Ricardo found is that actually you have to pay attention to any surface contaminants in the diamond samples. So basically, what we show in the top plot is a survey plot showing number of collected, so intensity of the photoelectron as a function of the binding energy. And most of the time, you're only looking at the large features, which is okay, fine. You're dealing with diamonds, so you have this carbon 1s peak, and then you're dealing with oxidized surface, so you have this O1s peak. And then if you really zoom in, you actually start seeing all these impurities. So you have silicon, sulfur. A lot of that's just come from, just breathing on your sample sometimes during processing. And we found a correlation between the oxygen percentage with the contaminants atomic percentage. And then furthermore, we actually found that like a byproduct that likely is one of the culprits is actually ammonium sulfide, which is actually a byproduct of one of the treatments that the community uses, which is sulfuric acid onto the diamond surface. So we found ways to get around that by doing a more rigorous rinsing and cleaning to clean up all of that. And then another thing that we found, and we have actually in this study tested basically about 8 different types of treatment methods, is a correlation in some cases between oxygen atomic percentage and the amount of sp2 carbon, and sp2 carbon is gravitized carbon. And so here we can separate the data into two different categories. Diamonds that have been treated with mineral acids, which actually the data is kind of a little bit all over the place in terms of a correlation with the amount of graphitic carbon, likely due to by some amount of etching during the treatment, that which depending on the etching time can lead to different levels of graphitic carbon. But then all of these lead to moderate levels of oxygen coverage on the surface. And then we tried a couple of dry oxidation approaches, which actually one is just UV ozone, and then the other actually uses an atomic layer deposition tool where we just send water pulses at some elevated temperature, and that seems to do a good job with oxidizing the diamond surface. And there we see a good relationship between the amount of oxygen that you find and the gravitization. But then overall, this gravitization is still a lot lower than if you were to treat the surfaces with mineral acid. And then one final observation that we had was that we took some diamonds and we further polished it so this is just with scape polishing that we sent out to a company that does it. And there we find uniformly that like your samples actually have a lot more gravitized content. And actually none of this actually is surprising given what some later evidence that we find in the literature. But what we've done in this study is basically shown a couple of factors that can really affect and conflate your oxygen content, and that might have led to inconsistencies in the literature. And in particular, digital mechanical polishing, which sometimes you need to do to make your diamond smooth enough for your sensing experiments, can actually increase in oxygen coverage through this increase in amorphized carbon, which has been actually studied in an ab initio study. And then we're also quite excited about these dry oxidation treatments, which seems to provide good oxygen content and low graphitic content. Okay, so then going back to this observation that basically no matter what we do for all of our oxygen treated samples, we see a good amount of sp2 carbon coverage. And so we wanted to study that further, but then the challenge is that it's actually really difficult to probe the top nanometer of like any material with conventional techniques. Like as an example, this is an illustration of our normal XPS configuration. You send in an X-ray, it penetrates pretty much through the diamond, and you have this collection and at some angle, and you're collecting basically over at least like several nanometers of the material. So then our solution to this in collaboration with Bob Hamer's group is to actually do an angle resolved XPS. And what that allows you to do is as you change the angle of your of where you're exciting of the X-ray beam that's hitting the sample, you get to probe like different depths. And this is a plot of the photoelectron escape probability as a function of sample tilt angle, which shows that as your angle becomes more and more shallow, you get to really probe small depths to basically some nanometers. And so we've done this, and we show that, like, okay, yes, as you change the angle, you get you see more and more of the oxygen functionalization and the graphitic carbon, and that correlates nicely. You have a nice correlation between the amount of oxygen that you're measuring and the amount of graphitic carbon. And then another knob that we use is the fact that you can actually look at different types of photoelectrons. We can look at photoelectrons from the core, so the core electrons, so the C1s. You can also look at the OJ electrons. And the nice thing about the OJ electrons is that the escape probability, it's that the escape depth is much lower than the core electrons. So that actually gives you another knob to even probe shallower to within the crystal. And so we've done that. And maybe just skipping over this particular detail is we look at the OJ electron and look at the best signature as a function of the angle of your XPS. And we basically found a transition between where you're predominantly diamond-like to where you are predominantly graphitic-like or sp2-like. And then that allows us to basically quantify the thickness of this sp2 layer, which is just a couple of monolayers. So it's about 0.4 nanometers. And so what we arrived at the end of this study is that, okay, so this is our previous naive model of what oxygen functional groups look like on diamond. And they consist of these nice ordered bonds. But what we find, at least for our surface treatments, is that it's actually a lot messier than that. So what we're dealing with is a very thin graphitic layer. And then within that, just oxygen functional groups that are kind of crammed into it. And so does it matter? I think this is a question that we are trying to answer, whether it matters for quantum sensing, because ultimately, maybe all we care about is having a good positive electron affinity close to your diamond surface. You don't really care about how well ordered your bonds are. And that's a question that we're trying to answer right now by doing spin coherence times and optical contrast measurements of various near surface NVs in oxidized diamond. Okay, so now switching gears a little bit, and I'll try to speed things up a little bit, is this second problem of limited photon collection, where there are two primary issues. One is that the dipole orientation of the emitter is actually not parallel to the crystal cut, which is typically what's optimal for light collection. If you're trying to collect light from a dipole in a dielectric, it would ideally be at well known, which is well known, but like at either at a parallel location, parallel orientation relative to the crystal cut. And then second is diamond has a relatively high refractive index at 2.4. So most of the angle at which you enter this condition of total internal reflection is relatively high. So then most of the light is stuck inside a diamond crystal. So first, I want to talk about how to properly actually understand this emission behavior. So the spin defects in general, they actually consist of electric dipoles that are orthogonal to the spin axis. So the emission that you get from color centers are not from like dipole emissions along the spin axis, but from basically the direction that's perpendicular to it. In the case of diamond, MV center is actually arising from a pair of electric dipoles, which I've labeled X and Y here. That you can think of the dipoles as just moving and emitting light, and it has to be perpendicular to the spin axis. But these dipoles have to also be perpendicular to each other, that they can be anywhere on this plane. And so then when you excite these dipole moments, you get emission out, so you get excitation. And what the picture looks like is the following. It's a highly temperature dependent behavior. So you have the ground state and you have excitation. In the excited state, you have then phonon relaxation between the two dipole moments. And then so in the end, you just basically get both dipole moments as an output at room temperature. And so then you basically can think of these two emission from these dipoles as being incoherently summed. So what you would get is something that's probably not the correct term to say, but it's some kind of single photon emission that's like unpolarized. Okay, so you can actually then model this radiative emission accordingly based on the model I just mentioned. And maybe skipping over the details, basically what we do is first calculating for near surface MVs as a function of the depth, what the perpendicular and parallel components of the dipole, how it would behave as you approach the surface. And then you just basically apply geometry to figure out for the actual dipole with that weird orientation of the spin relative to the surface normal, what the lifetime would be. Okay, so maybe skipping over to, oh yeah, one more thing is, as I mentioned, the MV emission is broad, so you need to do some spectral averaging, and then finally some polarization average result. But then what you get in the end is this. So you have the lifetime, radiative lifetime of these of the MV center at room temperature as a function of depth. And this is for 100 cut diamond. And what we find is that it will only depend on this depth as well as the spin direction relative to the surface normal. And so it would be great to actually experimentally validate this model. So what we did is we found one potential application, which is that in general, it's not that easy to find depth of these color centers after you've ion implanted them. There are a couple of good methods that have some drawback. So as I mentioned, typically we use ion implantation, which you can predict where roughly the ions would end up through a Monte Carlo software called SRIM. That it doesn't predict certain behavior like ion channeling. So you can actually do something called TOF sims to basically literally ablate the crystal to figure out where your ions are. And then there's also a nice technique based on nuclear magnetic resonance where you just put protons on top of your diamond surface, and then you basically use near surface MV as a probe for these protons, and then that allows you to extract their distance. But then this actually is a very small range effect, right? So like as your emitter gets farther and farther away from these protons, then you actually lose your sensitivity. So what we want to do is to actually try to see if we can, just by measuring, again, like in the theme of like all optical techniques, just by measuring radiative lifetime, can we actually get this information about the depth? So we made the sample based on a gradient implantation technique where we evaporated some implantation mass with a thickness gradient and then did ion implantation. And then we did lifetime measurements by sending in pulsed green excitation, and then that collects red fluorescence in a time-gated way. So then the output that we get is, so we actually have a fairly slow laser, so we have a fairly large instrument response function, and then the black curve you see would be like the raw lifetime gain. And so then this is our result. Basically, we took the longest measured lifetime in each region, where the thicker the germanium implantation mass, you expect the ions to be the shallowest, so the MVs to be shallowest, and therefore correspond to the longest lifetime. And then as you decrease the thickness of the germanium mass, you expect then the ions will go deeper into the crystal, and therefore your lifetime will decrease. So we're dealing with shallow MV, so indeed we have lifetimes that are longer than the average single MVs lifetimes in the bulk. And this actually corresponds to this part of our lifetime model where we have this slope of a change of about 0.14 nanoseconds per nanometer in lifetime versus the depth. And then we can convert that to a depth, which qualitatively, this data makes sense in the sense that we're expecting to find the shallowest MVs in the thickest part of the mask. But then we have a couple of drawbacks. One is right now our depth uncertainty is actually relatively large. It's at 5 nanometers, limited by the way that we're doing the measurement. And then we need an independent verification. So we're actually performing TOF-SIMS measurements right now to verify our data. Okay, so next, coming up with another application of this model of the dipole of the MV is basically trying to manipulate this optical emission through designing metasurfaces. So the idea would be to better extract light out of these MV emission. And in this case, this is work in collaboration with Mikhail Katz's group. Our group provides experimental support. We basically use an adjoint optimization techniques that optimizes for extraction of light from both polarization, both of these X and Y dipoles, in order to better extract light. So our structure consists of a thin layer of silicon on top of diamonds. So what the nice thing about this approach is that you avoid etching the diamond surface. Again, so that you're not degrading the near surface spins. So maybe skipping over this work, but then talking about our experiment, a recent experiment where we were able to demonstrate this with just a very simple silicon pillar that you can fabricate in place on the diamond surface. And this was done using a membrane transfer technique. So what this silicon pillar does to near surface MV is increase the extraction efficiency by about a factor of 7 based on simulation if it is correctly placed. And also it helps beams the light into a lower NA collection optic. And so maybe skipping over, in the interest of time, the fabrication and just talking a little bit about the results. So we have, so yeah, this is a picture of the silicon pillars that we're placing on top of the diamond crystal, and then underneath the diamond crystal, within the diamond crystal contains ion implanted very shallow quantum emitters. So this is what the sample looks like before you did this fabrication. With the absorption of silicon, you can't quite see the emitters, and then afterwards you actually see these arrays of spots that light up. Not all are MV center emissions. Some are we're just actually enhancing the background, which is not what you want. But we actually, for a couple of pillars, we actually found nice enhanced single photon emission. So we confirmed that with second order autocorrelation measurements, with a saturation measurement where we're just taking light in, light out measurements, confirming that we're getting higher counts. And then we also saw some shortening of lifetime. So there's a slight bit of percent enhancement on top of that, changes in the extraction, in the beaming of the emission. So now maybe in the last 2 minutes, I want to talk about, in general, leveraging of this silicon on insulated platform for metasurfaces that are maybe ideally suited, that are well suited, and for any emitters in the near infrared. So if we look at, this is a plot of the refractive index and loss of single crystalline silicon as a function. I think this is about a 500 nanometer thick silicon. As a function of wavelengths, you see that you get nice high refractive index well over 3.5 and comparatively low loss. And so even though this will not get you, the longest propagating waveguide, you actually get to make pretty nice low quality factor photonics using this platform. And one of our group's recent work is to demonstrate this by making a silicon on sapphire metasurface polarizing beam splitter that we use in combination with a vapor cell magnetometer based in rubidium. And so this is actually a picture. So I'm happy to go over later how we designed a metasurface. But basically, we made a metasurface comprising of these silicon pillars on the transparent substrate, in which the idea is to have it act exactly like a polarizing beam splitter. And then we put that in an atomic magnetometer setup where we show magnetic sensitivity of below nanotesla. So I think I'm almost out of time, but what our lab, what we're trying to go from this is basically kind of leverage advances in silicon photonics and also integrated electronics in order to miniaturize the lab scale quantum sensors that are right now performing really well, but we'll need a lot of engineering solutions in order to deploy out of the lab for various applications, like putting on mobile platforms and onto some various sort of ground surveys. And we're looking into integrated electronics for this purpose, as well as integration of cold atom structures with gratings. And maybe I'll just end here and thank you for your time, and also just summarize by saying that I hope we've conveyed that atoms and spin defects provide a nice spectrum in terms of the spatial scales you can access, from atomic nanoscales to maybe micron millimeter scale with co-atoms to more macro scales. We've shown some surface control and diagnostic techniques. And then we're quite also excited about a silicon-based photonic integration of these quantum sensors in order to push them to better functionality. So thank you very much. Yeah.
I'm wondering whether or not you have to start worrying about the signals from that and how they cross out on the sensors, basically. They're making things much smaller. The wires themselves are making magnetic fields and charging effects.
Yeah, I think that's certainly a concern, especially for vapor cell magnetometers and for the application of looking at magnetoencephalography, where you need like multi-channels and you need minimal crosstalk, and which is why I'm quite excited about any optical techniques where you can get away from any RF and most electronics, and maybe even with fiber integration, you can have all the detection be far away from where the sensing is taking place. Yeah, that's a really good question. I completely glossed over it. So for this particular sample, we're using a very shallow, very low energy implantation, but probably based on SRAM, which is not very reliable, the location of the emi is around 6 to 10 nanometers, but that's the mean. And so that's just the vertical straggle, right? There's also lateral positioning. And so we think that the fact that what we have observed in terms of enhancement, which is a factor of 3 as opposed to 21, which is predicted in our model, is completely because of that, just that we didn't get close enough to the meta surface, and also laterally we didn't position it well enough. Hi. Thanks. Yeah, so that's the picture that we have based on our angle resolved XPS data. And we find that basically for any oxygen treated sample, sp2 is just pervasive. Like there's almost nothing we can do to completely get rid of it. If you start off with a hydrogen terminated sample, I think that's probably a route towards starting with a very clean, well-ordered surface. And then after that, you can treat it with some kind of carboxylic acid, like Bob's group does, and that could help. So we have limited success so far in doing that, because what we find is that we're not effective in removing all the CH bonds. So actually, we're interested in doing a spin study where we have partial coverage of the CH and then maybe really low level of sp2 and overall slightly positive electron affinity, and see if the MVs are happy. Yeah.
And a follow-up question. Your lifetime.
Yeah. Yeah, so I think that's the part where it's a very good question, because we did not do a good job separating out the effect of quantum yield in this study, which is why we really need an independent measurement, which we're hoping to do in a couple of weeks with TOF-SIMS. Yeah. Mm-hmm. Oh, yeah. So basically, yeah, we thought of it, but then what we're hoping to also do is like get away with not doing anything. But that's a really good point. There's a good work by I think Ulrich Anderson, where they actually basically try to measure the quantum yield and image the photonic density of states by doing exactly that, like doing that scanning with a plasmonic particle. Yeah. Thank you very much.